Assalamualaikum warahmatullahi wabarakatuh and good morning everyone. So this is week number 3. We are going to discuss how to derive the compatibility equation for two redundant beam. And after that we will try to solve analysis of frame with two redundant. Okay. Okay, let's look at the module under 2.3, two redundant beam. Degree of indeterminacy for two redundant is 2, means there are 5 unknown reaction. There are 5 unknown reaction we get from support. Okay, so remember, to determine redundant, we have to find the difference between between unknown reaction and 3 equilibrium equation. 3 reaction that can be solved using 3 equilibrium equation. Okay, by looking at figure 2.4 here, okay, this is an indeterminate beam with two DOI. Okay, there are fixed and 2 rollers. So in total, there are 5 unknown reaction. So here we have 5, 1, 2, 3, 4, and 5. So 5 unknown reaction and only 3 can be solved using equilibrium equation. So there are 2 redundant. And these 2 redundant we need to remove from the system to get the primary condition, the primary structure. We need to remove. So in this case, when there are 2 redundant, we have to label R1 and R2. So we have to choose what is R1, what is R2. So we have to remove 2 from the system. Okay. So again, when we want to derive the compatibility equation, we will based on the principle of superposition. And for the principle of superposition, it is start from actual beam equal to primary beam plus redundant 1 plus redundant 2. Okay, it is actual beam is equal to primary beam plus redundant 1 plus redundant 2. Okay, so looking at this example, redundant 1 R1, BY is chosen as redundant number 1, CY is chosen as redundant number 2. Okay, so we have decided that BY and CY will be removed from the actual system. So when we remove BY and CY, we will get the cantilever beam fixed at A. Roller B and roller C we remove from the system. So that is why here we label R1 is equivalent to BY, R2 is equivalent to CY. Okay. So from the principle of superposition, so since this is R1, this is R2, okay, primary beam plus redundant BY applied plus redundant CY applied equal to actual beam. Okay, so what we need to do is we have to focus on the two redundant position. We have to focus on two redundant position. Okay, the position is located at B for redundant 1, and the second position is located at position C for redundant 2. So we will have to draw the deflection. The deflection in actual beam. So at B in actual beam, here is delta B is equivalent to 0 and delta C is equivalent to 0. Delta B 0, delta C 0. Delta B 0, delta C 0 in actual beam because of the support. Okay, so we can see in the diagram when we draw deflection, okay, it's going to be like this, going back to 0. Okay, because at support, displacement or deflection is 0. Okay, so move to second one. It is called as primary beam. Whenever we remove both redundant, we have to remove BY and CY. Remove BY and CY, so we will get the primary beam. We get the primary beam. And now we have to focus on the displacement that is occurred at two position. At two position, we have to focus to position B and position C. Okay, so this is cantilever beam. This cantilever beam is subjected to UDL along member BC. Okay, due to the UDL, the beam will deflect, okay, and we have to focus on displacement or deflection, okay, occur at B and C, okay, and we have to label that. So how are we going to label this? Remember the tips. We are going to calculate deflection at position B, so we label as B. For primary beam, B naught. Naught is labeled for primary system. Naught is labeled for primary beam. Okay, the first notation is for position, the second notation is for type of beam. Okay, for you who join this session, please tick your attendance in the U future. Okay, right now. Okay, don't forget to tick your attendance in the U future. Okay, continue. Okay, the second position is C. The second position is C. So deflection at C means delta at C for primary beam. So we will label as delta C naught. Delta C naught. Deflection at position C for primary beam. Deflection at position C for primary beam. Okay, so we have to actually determine the displacement which is located at B and at C for primary beam. Okay, primary beam is a determinate beam subjected to all external loading. Okay, means that the loading remain same like actual beam. Okay, we remove only the support, the redundant. Okay, so next we have to plus with redundant 1 plus with redundant 2. Plus redundant 1 plus redundant 2. Okay, next is plus redundant BY applied. Plus redundant BY applied. So this is redundant 1. This is redundant 1. Okay, redundant 1 means it is a cantilever beam subjected to a unit value. Okay, of BY we put outside. Means that everything inside the system we have to times with BY. Okay, not only 1 times BY. Deflection also we have to time with BY. Reaction also we have to times with BY. Okay, so this is a cantilever beam subjected to a unit value. And remember, whenever it is a redundant diagram, the delta or the theta, we have to use F. F is stand for flexibility coefficient. F is flexibility coefficient. So we use F. Okay, so due to a unit value at B, due to a unit value at B, due to a unit value of at B, so at position B, so the label will be used is F F for displacement due to a unit value. F is displacement based on a unit value. Okay, displacement at position B for redundant BY applied. FBB means due to a unit value, deflection due to a unit value. At position B, for redundant BY applied. So we label as FBB. FBB. Okay, next we move to position C. We move to position C. Again, F at position C. F at position C. So that's why we get FC. FC. At position C for redundant BY applied. So we label as FCB. FCB. The first notation we use for the position, the second notation we use for type of beam. So this type is redundant BY applied. This is redundant beam. This is for redundant number 1, redundant BY applied. We take B. Okay, that is why it become FCB. Position C, redundant BY applied. Okay, so this is redundant number 1. We have to plus with redundant number 2. We have to plus with redundant number 2. And redundant number 2 is CY. Redundant number 2 is CY. So this is R2. Redundant number 2 is CY. So we are going to use the label of C. Okay, for the redundant, for type of beam. Okay. Okay, we have to measure at each system in the in actual beam, in primary beam, in redundant 1 and in redundant 2, means in all systems. We have to look at the displacement occur at 2 redundant position. So we will have to find 2, 2, 2. Primary 2, redundant 2, redundant 1, 2, redundant 3, 2. Means there are 6 displacement. 6 displacement that we are going to determine. 6, 2 in primary beam, 2 in redundant number 1, redundant BY applied, and another 2. Okay, we will determine in redundant number 2. 2, 2, 2. So in total, there are 6 displacement. 6 displacement, which is equivalent to 0 unless the support settlement occur. Okay, so due to a unit value of CY, okay, it is 1 times CY equal to CY. But don't forget, CY representing the whole. Means that displacement also we have to time with CY. Reaction at support also we need to time with CY. Okay, so due to a unit value, at position B, we label as F. Due to a unit value, in the redundant diagram, we label deflection as F. And for the first is for the notation, the first is for the position. The first is for the position. So at position B, diagram, the diagram is redundant CY applied. So that is why here we use FBC. FBC means due to a unit value. This is displacement due to a unit value at position B for redundant CY applied. That is why we label as FBC. Okay, next one is at position C, redundancy. At position C, redundancy means CC. At position C, redundancy means FCC. FCC means due to a unit with deflection due to a unit value at position C, redundant CY applied. Okay, so this is the general equation. Okay, don't forget to tick your attendance in the U future. But before that, I also want you to scan QR code. Okay, we take a short, okay, a short break. Okay, for giving you time to scan this QR code. Okay, so I want you to scan this QR code. Okay, I only see 16 of you. Where are the other 4? So if you want to join using website, using browser, you just take class. You just use classpoint.app, classpoint.app, and the class code is 44219. 44219. Please scan this QR code. Okay, for your attendance evidence. You get that QR code? Okay, please scan. Okay, classpoint.app, classpoint.app 44219. Please scan the QR code or use the link to join. Okay, you can swipe to another apps from your phone, and maybe you can use browser. Okay, the URL is classpoint.app. The class code is 44219. Okay, I can see 2 of you here. 99. It is 699. 699 646 602 324 876086 800 506. Okay, now 6, yeah. Okay, 7 8. Okay, 12. I want to see 20. Okay, don't forget to tick your attendance as well in the U future. Okay, Arif Iskandar, Muhammad Mukri, Nur Amira Bahiyah, Nurul Natasha, Siti Fatimah. Okay, 13 has joined. Fifteen now. Sixteens. Okay, you should be 21, 21. Okay. Okay. So we go back to the OneNote here. Okay. Okay, so we are going to write the compatibility equation. There are two equation because of two equation because of two redundant. Equation number one is based on the displacement at position B. Equation number one, redundant one, location is B. And equation number two, redundant is CY, location is at C. So there will be two equation. We start with, okay, just focus on the position, the redundant position. We start with B first. Okay, it is actual beam. Actual beam equal to primary beam plus redundant. Okay, I remove this first. Redundant BY applied plus redundant CY applied. Okay, just look at the displacement at B in all system. Start with actual beam. Okay, so remember the general equation. Actual beam is equal to primary beam plus redundant BY applied plus redundant CY applied. Redundant BY applied. Redundant CY applied. Okay, position. This is position. B. Okay, delta B naught means deflection at position B for primary beam. FBB is deflection at position B for redundant BY applied. FBC is deflection at B. Okay, deflection at B, redundant CY applied. Okay, so this is how the equation look like. This equation is based on the principle of superposition. Okay, we will do the same for position number 2, for redundant number 2. And redundant number 2 is located at C. And it is delta because BY and CY is force. Force means the partner is delta. Force, the deflection here induced by the BY and CY. Okay, so move to the second equation. At position C means delta at C. In actual beam. Okay, delta at C in primary beam is delta C naught. Delta at C in primary beam we label as delta C naught. And we have to plus with, remember C, when we start C, so means that here will be C, the position, C, redundant, BY. Okay, deflection at C here, deflection at C in the primary beam, we have to plus with F at C times with by. That is why we write FCB by. So this B belong to this B, representing B, by. The second one is for the for type of beam, redundant by applied. Okay, and next one is F at position C, redundant cy, FCC. So we get plus F position C, redundant cy. Means that this is C here, C. Okay, redundant for second notation. Okay, to represent type of beam, the redundant beam, FCB means the last B representing by, and FCC, the last C representing cy. Okay, so this is the two equation that we get from the principle of superposition. We name this as compatibility equation. There are two equation because of two redundant. So when we have three, for example, three redundant, we will have three equation. Okay, and by looking at these two diagram, okay, this is redundant for redundant 1, this is for redundant 2, produces, okay, the two equation. So looking at this diagram, in actual beam, because of the support, the original diagram, delta is equal to 0. So delta B in actual beam is 0 because of the roller support. Delta C is also equal to 0 because of roller support. Okay, so we will rewrite back this. Okay, rewrite back this equation in matrix form. Start from primary system, and this is equivalent to 0. Equation equal to 0, not 0 equal to equation. And we will write the compatibility equation in matrix form. Okay, we will group the displacement in primary system together, and we will group the four F, okay, together. The four displacement in the two redundant system together. Okay, and since there are two redundant, we will have 2 by 2 flexibility matrix. Okay, so we will rewrite this back to the form, the new form of compatibility equation. Okay, it is going to be like this. Okay, it is delta B naught, delta C naught. We group this together. Delta B naught, delta C naught, delta B naught, delta C naught. So we group this together. These two are displacement in the primary structure. Okay, so B naught, B means redundant 1, C means redundant 2. Okay, we after that we group the four flexibility coefficient together. Okay, because of two redundant, we will get 2 by 2. When we have three redundant, we will have 3 by 3. We group together. So here in the matrix, so we have to apply all the matrix characteristic. Okay, so this is F, 4F, 1, 2, 3, 4. It is 2 by 2. 2 by 2. Okay, 2 by 2. So it is FBB, FBC, FCB, FCC. Times with the first redundant is BY, the first redundant is BY, the second redundant is CY. And this is equal to 0. Okay, so we group the deflection in two redundant beam together. Okay, we will have 2 by 2 matrix, 2 by 2 because of two redundant. So F is for flexibility coefficient. So F is in this case is deflection. So how to label? Okay, how to label? We just need to follow here. So this is B, B. Okay, BY, redundant 1. Redundant 1. And then we have C, delta C naught. C, C, C. Okay, and then when we check back, so matrix multiplication FBB times BY, so we get this. And FBC times CY, we get this. So we can conclude that the standard form of compatibility equation for two redundant or for three redundant, we will write in matrix form like this. Okay. Okay. So this is the standard form of compatibility equation. And now from this, we will rewrite it back into a standard form of compatibility equation. We now replacing R1 BY, R2 CY. Okay, now we will change the label of notation from ABC, from BC to numbering. From BC to numbering. Because when we use BC, it is just specific for this particular question. So when we have standard form of compatibility equation in numbering, we will apply the same equation to all type of structure. We can apply this to a different type of redundant. We can use the same compatibility equation for the other type of structure and the other position of redundant. Okay, now from the upper compatibility equation, we will now rewrite the equation back by changing label B to 1. And we will change label C to 2. Representing first redundant, second redundant. First redundant, second redundant. Redundant 1, redundant 2. Redundant 1, redundant 2. We will rewrite the equation. We write the equation and what we get is like this. Okay, so all B that we find in the compatibility equation, we replace by number 1. 1 for redundant 1. 1 for redundant 1. Okay, and all C we replace by 2. All C we replace by 2. So what we get is the standard form of compatibility equation, which is look like this. Okay? This is the standard form, and everyone has to remember this standard form of compatibility equation. Like this, the standard form. And this is for the redundant 1 and redundant 2. Means that if the moment is redundant, so this is moment. Okay? Maybe this is CY. So it can be changed according to the condition. Okay, so this is the standard form of compatibility equation that everyone should understand and should remember. Okay? Should remember. So go back to this. So this is all the meaning, the definition. Please read. Okay? And as usual, the delta and delta B naught, delta C naught, FBB, FCC, FBC, FCB is actually representing displacement, and we use integration of two moment equation to calculate the value. Okay, and due to that, we just need to use the notation. So if it is B naught, B naught means MB M naught. If we change the label to 1 naught, means it is M1 M naught. Okay, so this is all the formula, and I believe everyone have understand about this formula. Okay, so this is the compatibility equation, which we derive, okay, from the displacement in the two redundant position, and we change the label, the redundant one. Okay, instead of using ABC, we change to number one, and same goes to redundant number two, so we will label as two. So what we get is the standard form of compatibility equation, we write like this okay, and you have to remember this. Okay, you have to remember this. F is flexibility coefficient. Okay, so you just don't get confused, because in order to calculate the value, we just need to refer to the label that we use. Okay, inside this we can see label 0, 1 and 2. 0, 1 and 2, or not 1, 2. Okay, inside this, these are the 6 displacement. Okay, delta 1 naught, delta 2 naught, F11, F12, F21, F22. These are 6 displacement which come from 3 system, and each system we have to look at the two position of redundant, two displacement. Okay, 6 displacement, and labeling or notation that we use here, that we can see here, is 0, 1 and 2. So we find that we have 0, we have 1, we have 2. What does it mean? Okay, in order to calculate displacement, for beam and frame, so we will write the moment equation. Which we label by M naught, M1, M2. This is for beam, this is for frame. For bending effect, we integrate. Okay, when we consider bending effect, means EI, we have to integrate moment equation. Okay, so there will be M naught, M1, M2 represent primary system, redundant 1, redundant 2. Primary system, redundant 1, redundant 2. Okay, so for the formula, we just need to refer to whatever notation that we use. You don't need to remember the whole. Okay, you just need to understand, okay, from the derivation and how we get the 0, 1, 2 label. Okay, so this are all the formula, the standard form: delta 1 naught, delta 2 naught, F11, F21, F12, F21, F12, and F22. Okay, it is two moment equation. So for 1 naught, we use M1 M naught. 2 naught, we use M2 M naught. 1 1 means M1 square. 2 1 means M2 M1. 1 2 equivalent. So this is equivalent. M1 M2 and F22. So 6 value, 5 times calculation, because F12 and F21 is the same. Okay, Okay, I have also explained about what just I say what this. Okay, this is one example in the module. So since I said that, okay, so you can also refer to this illustration. I have drawn this to you representing the principle of superposition. Start with actual beam equal to primary beam with the reaction, redundant By applied with the reaction, and redundant Cy applied with the reaction. So all this, from this we will have the moment equation. The moment equation we summarize into the table. And we calculate the displacement. We calculate displacement, and then we substitute displacement into the compatibility equation. So we will solve this using calculator. It is equivalent to two simultaneous equation. Okay, we solve the compatibility equation for forces By and Cy. So we get these two value for By and Cy, and after that we get the By and Cy. Okay, so once we get By and Cy, we can continue to calculate remaining reaction, and we actually have two choices. Either we will continue to calculate reaction using equilibrium equation, the three remaining reaction, or we can have another option. Another option is we can determine the three remaining reaction in actual beam using principle of superposition. Using principle of superposition. Why we can do like that? Okay, just look at back to this. Okay, we have primary beam. Where we have the reaction 240 and 1600 negative. This is the reaction in primary beam. And in redundant By applied, we have reaction -1 and 5. Okay, and all this, don't forget we have to times with By, the value that we get. Okay, and we also have the reaction due to a unit value of Cy, means that this reaction we have to times also with Cy value. So what we get is we use the principle of superposition. Okay, not only for the compatibility equation, but we can also use the principle of superposition to calculate remaining reaction, and this is easier than using equilibrium equation. Okay, Ma means, okay, this is -1600, means the value in primary system. Okay, 5 is the moment in redundant 1 times with redundant 1. And this is Ma in redundant number 2 diagram, and this one we have to time with R2, means Cy. Okay, so we get 163.01 is actually the moment equation in actual system. Okay, same goes to Ay, remember, so this is R1, this is R1, this is R2. Okay, so in redundant system we have to times back with redundant value. Okay, so 240, this 240, -1 and -1 is Ay in primary system, redundant 1 and redundant 2 respectively. Okay, so we get all reaction. And after that, for checking, if you want to check for the equilibrium, we can use equilibrium equation, and this is just option. Okay, we just need to check before we draw the diagram, because whenever it is correct, you will get 0 for total Fx and total Fy. If you don't get 0, means there is something wrong somewhere. Okay, and from this you can actually continue to draw the shear force diagram and the bending moment diagram. Remember, when we draw shear force diagram, we just need to focus on the shear value, means all the vertical forces in the diagram. Okay, so the vertical forces here is this 97, 325, 40 times the length, and 12.325. 12.325. So all these are the vertical forces. So this is the diagram, the shear force diagram. The shear force diagram. We start with zero. And we have to minus by 97.812. So this is the position of negative. And then we have to go straight until we meet this 325. So going up from this point plus 325, so we meet 227.675. 675, and then we have to minus by 40 times the length. I'm not sure what is the length. The length is about 5. Okay, the distance it is 5 or 6. Okay, so we get 5. We get 12. Okay, this 12. Okay, negative 12.325, and looking at the arrow, okay, we have to plus. Okay, and this is the last position. This is the first position. This is the last position. Close the loop. Close the loop. And from the shear force diagram, we can draw the bending moment diagram from the area of shear force diagram. Because shear force is in kilonewton. Okay, time with the distance. Okay, we get moment. Kilonewton meter. So now when we want to draw the bending moment diagram, we have to look at the moment value. Moment value, okay, and as well as the area of shear force diagram. We start with zero. Okay, we should start with not zero. We should start with 163.01 for A. Here is the position 163.01. Okay, we have to minus by the area 97.812 times 5. Okay, we have to find the value here. Okay, and it should be straight, not curve. It is straight line. Okay, we get the value from the area of shear force diagram. I don't calculate it here. Okay, this is how it normally look like for the shear force, for the bending moment diagram. And you have to get this value from the area of shear force diagram. Okay, and after that, for the shear force diagram, when there is an intersection, shear force diagram is zero, means there are maximum moment. So we have to determine the distance. Okay, the distance at intersection from the shear force diagram. Okay, we get 0.308 and 5.692. Okay, and then this 320, because there is a value here, we have to consider. Okay, so the value is going to be somewhere here or somewhere here. Okay, if it is negative, right? Negative, maybe dekat bawah lah. Okay, so the next position is we get from the area of triangular, the first triangular. Okay, and then we will get the value normally like this. Okay, and then the last value, since at C is not fixed, it is roller. So the moment is 0, so we should get 0 back. So here we have to have the bending moment diagram like this. And from this and this. Okay, so this is how the BMD look like. Okay, this is how BMD look like. This is positive and this is negative. Okay, so please try to do on your own. So every question under topic 1, topic 2, topic 3, you have to get familiar with how to draw the shear force diagram and bending moment diagram. And actually you don't have to write shear force equation in order to draw the shear force diagram, and you don't have to write moment equation in order to draw bending moment diagram. Okay, you can draw directly like this from the diagram with all the forces inside. You can straight away draw the shear force diagram, and from the shear force diagram you can continue to draw the bending moment diagram from the area of shear force diagram. Okay, so this is beam analysis using flexibility method. Okay, so let's move to next. Okay, I just want to go through what example is given in the example and question is given in the module in the workbook. Okay, this one is too redundant. You have to write the flexibility coefficient, flexibility equation. Okay, this question, the question is write flexibility equation. Write flexibility equation means compatibility equation. So compatibility equation has two names. Another name is flexibility equation. Write flexibility equation for the beam means the in the matrix form, the standard form of compatibility equation, we find the value, find the displacement and fill in into the equation. That's the answer for A. Determine reaction at all support. Okay, when we solve the flexibility equation, we get the redundant, and we solve the remaining using either compatibility equation, using either simply uh, superposition method or equation of equilibrium. And after that, you have to continue to draw shear force and bending moment diagram. So this is just to enhance your skill. Okay. Okay. I put one calculation sheet here for you to draw the diagram. Okay. Two redundant as well. Okay. Under 2.2.3, two redundant beam. These two redundant beam, you can see that the question look like similar. However, under 2.3.3, this is support settlement question given in the question. Support settlement. Support settlement question. Support settlement question. Okay, redo the analysis. Choosing CY and DY as redundant means R1 is CY, R2 is DY, but now there is a support settlement. Okay, support settlement occur at C. Occur at C. Occur at C. Support settlement occur at C. Delta C lah. Support settlement occur at C mean delta C is equal to 30 mm. 30 mm. 0.03. 30 mm downward. Okay, so from this we will have to write the compatibility equation, the standard form. This is for R1, this is for R2, and displacement occur at at position C in actual system. So normally support settlement will only affect the actual system. Support settlement only affect, this is actual system, right? So this is for support settlement. So for support settlement, it only affect the actual system. So you don't have to be worried. Support settlement does not affect this part. Okay, support settlement we have to put at actual system. Okay, so after that you have to do calculate it as usual. So you will get the new value of redundant because of the support settlement. Okay. So this is another question, another example given. Another example given. Okay, so please answer, try to answer this because I have put guidance how to solve it step by step. You just need to follow. Okay, you just need to follow, label, choose redundant, what is the equation, so what is the next step, the second step, and then the equation, the table also given to you. Okay, you just need to define your origin and limit, put the moment equation, and then you have to calculate displacement and write the compatibility equation. Solve for the redundant, and then calculate remaining reaction. Okay, checking. Okay, so I want to choose one frame question to do exercise for today. One frame question. Okay, we move to frame question. This is one redundant. I want to do two redundant. Okay, for the rest, you have to do it on your own. Practice, practice, and practice. A lot of practices. Okay, in order for you to enhance your skill and understanding. Okay, this is one redundant. So one redundant. Okay, this is two redundant. Okay, this is two redundant, problem 3.6 under 3.3.1. Okay, for those who have the module, the ebook right now, the module, so please refer to uh, this subsection under 3.3, 3.3.1, problem 3.6. Okay, second degree of indeterminacy is two redundant. Second degree of indeterminacy is two redundant. Okay, so this is the diagram. Okay, this is the diagram. Okay, we take a break about 5 minutes before we continue to frame question. Okay, too redundant. Okay. Assalamualaikum. We are coming back. So what I want you to do next now is to follow the instruction. Okay. On your phone after this. On your phone after this. Okay, I will use the class point to give you activity and you just have to follow the instruction given. Okay, please do step by step and upload into the class point using your device. Okay, so start with the first step. We determine the redundant. Okay, redundant forces for 5 unknown reaction. We have to redundant, and actually you have to be free to choose wherever which redundant that you want to remove, as long as the frame will be determinate frame. So you can remove either two from pin, or you can also remove one from fix, one from pin to become one pin, one roller, or you can also remove two from fix and two from fix, so it will become one roller, one pin. Okay, remember the primary frame, it is a determinate frame, okay. You have to make sure that the system must be either one fixed end or one pin, one roller to become stable and determinate. Okay, I want you to do and upload. Okay, so I will end the live session right now, and I want you to focus on your device. Okay, to answer whatever question appears later on. Please do on your own paper, and then snap the answer and upload. Okay, step by step, one step by one step. Okay, we will do this about half an hour. Okay, so thank you very much. We will continue. Okay, as I mentioned. Assalamualaikum warahmatullahi wabarakatuh.